All right, good morning, everybody. So, today we're going to move into Chapter 3. But before we do that, let's review quickly Chapter 2. So what were the big things that we learned in Chapter 2? IR spectra, which is a technique, right? And allows us to, what's the next big thing that we learned?
Identify functional groups.
Functional groups, right? So we learned about functional groups and we learned how we can identify them experimentally. And so how many of you are continuously studying those functional groups? You've got to keep doing that. You've got to have these committed to memory, okay? You've got to be able to identify a functional group in a molecule, regardless of how big or how complicated it looks. You need to be able to go through and say that's an ether, that's a sulfide, that's a thiol, that's an alcohol, that's a carboxylic acid, so on and so forth, okay? So everything that we do from this day forward assumes that you have a thorough understanding and being able to identify functional groups. Today we're going to get into Chapter 3, where we're going to start talking about reaction mechanisms. So one of the questions we're going to answer is, what is a reaction mechanism? What do we mean by a reaction mechanism? How a reaction occurs. That's right. So in general chemistry, right, you all talked about acids and bases reacting to form salts and water, and you largely ignored how that happened. You spent a lot of time talking about equilibria and energy and enthalpy and entropy. All those things are important, but it doesn't really tell us how, step by step, that reaction occurs. How do reactions occur in general? What has to happen for a reaction to occur? We have to have bonds breaking, we have to have bonds forming. And can that happen if two atoms or two molecules are separated by a distance? They have to come together, right? So we're talking about collision theory, right? And it turns out that in organic chemistry, we can largely think about these reaction mechanisms using a process known as arrow pushing. And arrow pushing is a formalism, okay? And it is part of the language of organic chemistry that you all are going to learn. You are going to become proficient at arrow pushing by the time you leave this class in 256. Day one, I promise you, you will not get it as well as you think you should. It takes time to develop that skill, and we'll allow you the time to develop that skill, okay? We're going to talk about acids and bases today. What kind of acids and bases do you all know about? Name some for me. Name an acid. Hydrochloric acid. What's another one? Pardon? Phosphoric acid. What's another one? Sulfuric acid. Give me, before I had hydrochloric. Carbonic acid. Okay. What else? Think about your acids. Already been mentioned. Yep, but that's true. What else? Nitric acid. Yeah. Any others? Now think about the bases that you know. What bases do you know? Give me some bases. Ammonia. Okay. What else? What bases did you use in Gen Chem all the time? Sodium hydroxide, potassium hydroxide. Any others? Those are pretty much so the bases that you talked about. We're going to expand the definition of base and acid in this class. Most of what you've been dealing with are proton donors and proton acceptors, more like the Arrhenius theory of the Arrhenius and the Bronsted-Lowry type theories. We're going to focus on the Lewis theories of acids and bases. They're very, very important to think of things in terms of Lewis acids and Lewis bases. And it turns out almost all organic reactions, not all, but almost all of organic reactions can be thought of as nothing more than a reaction of an acid and a base. Okay? And so if you can identify an acidic site and a basic site within functional groups, you can usually get a good, strong sense of how the reaction occurs. Okay? We're going to talk a little bit about what alters acidity. Most of the acids that you all listed to me, except with the exception of carbonic acid, I believe, are strong acids, because in general chemistry, that's what you focused on. A strong acid and a strong base react to give me a what? A salt plus water. You will not have that type of simplicity in organic chemistry. An acid and a base react to give a new compound. Rarely is it a reaction that results in water and a salt, okay? Although that can happen as well. And so we're going to talk about what alters acidity. What makes an organic acid stronger or weaker? What makes an organic base stronger or weaker? Okay? And actually there are some organic bases that are a heck of a lot stronger as a base than sodium hydroxide. You all learned that sodium hydroxide is a base and a strong base. In organic chemistry, it's a very weak base. We have bases that are so strong that if you put them in the presence of air, they spontaneously burst into flames. That's a really strong base, okay? And so we're going to talk about some things that go beyond your general chemistry concept of a strong acid and a strong base, okay? Typically, organic reactions fall into four main categories, okay? There are others. We're going to be talking about substitutions. We're going to be talking about additions, eliminations, and rearrangements. Those are the four reaction types that we are going to hammer all the time, okay? We're constantly going to be talking about substitutions, additions, eliminations, and rearrangements, okay? Now that is a reaction category. That is not a reaction mechanism. So for example, if we look at these two reactions, both of these reactions are in the substitution reaction category, okay? Why would this be a substitution? Why would you tell your friend that top reaction has to be a substitution? What's being substituted? All right, so yeah, so we're substituting one functional group for another, if you will, right? So we're starting off with an alkyl halide, and we're ending up with what? An alcohol. So this tells us that I can take alkyl halides, react them with sodium hydroxide, and I can get alcohols. That is known as a functional group transformation. That's the power of organic chemistry. I can take one functional group that I'm given and I can transform it into something that I want, okay? I can take an alkyl halide and I can convert it into a needed alcohol through a substitution reaction. I can take an aromatic compound, let's just suppose this is benzene, and I can react it with bromine in the presence of iron, and I can get an aryl bromide, or an aromatic halide, if you will. That is a functional group transformation. What is being substituted? Okay, we're replacing the hydrogen with a bromine, right? Substituting one for the other. I'm going from what is the aromatic, what kind of functional group is that? Obviously it's a phenyl ring, right? But what category of molecule is it? It's made up of what? Carbon and hydrogen. It's a pure hydrocarbon, right? And so we're transforming a pure hydrocarbon into a halide, okay? Both of these are substitutions. Both belong to that class. The reaction mechanism for both of those reactions is completely different. How you transform an alkyl halide into an alcohol is a heck of a lot simpler mechanistically than how you take an aromatic hydrocarbon and convert it into an aryl bromide. The mechanisms are vastly different, okay? Additions. Why would you say this is an addition reaction? 2 to 1. What do you mean by that? Okay, that's right. We're adding a molecule to another, right? These reactions are considered to be ideal. Why do we consider them ideal? Why, if you were a company, why would you love doing addition reactions as opposed to substitution reactions? Well, that's right. There's no waste. Everything that I put into my reaction pot comes out in my product, right? So I buy a train load of alkene, I buy a train load of bromine, mix them together, I get 2 train loads of product that I can sell to my customer, right? That is not true in the substitution reaction, is it? In that top example, if my company is making this alcohol, I'm making the alcohol, but I also now I have to deal with this byproduct called salt, right? Fortunately, salt's not too terribly difficult to deal with, but it's still something that my company's going to have to deal with. I'm not in the salt business, right? I'm in the alcohol business. And so what am I going to do with that? But if I'm in the dihalide business, this is great because I can take an alkene, which I can purchase, I can take bromine, which I can purchase, and I can make a product that I can sell. This concept you all need to know about. It's called atom economy, and it's something that chemists are talking about all the time. This was a term coined by Barry Trost, who should win a Nobel Prize in my opinion, Stanford, and he published this in the early 90s in Science, this concept of atom economy, where it's kind of a green approach to chemistry. How do we minimize byproducts? How do we minimize waste? Addition reactions are an excellent example of this. Everything that we have in the starting material side ends up in the product. That is an ideal reaction. Do you think the mechanism for this is the same as the mechanism for substitution? No, it is not. Okay? Eliminations. What are we eliminating here? Okay, in general that's true, but exactly what am I eliminating? What atoms am I eliminating? I'm eliminating a hydrogen and a bromine, right? I'm eliminating HBr, right? This is an elimination reaction. It requires a base for this reaction to occur. But I can eliminate the elements of HBr and get an alkene plus potassium bromide plus water. All reactions are technically reversible, right? So what would be the reaction type in the reverse of an elimination? An addition. So just by looking at this, I should also know that I can take an alkene and add HBr across that double bond to make a new product in an addition reaction, okay? So what's the functional group transformation? What functional group am I starting with? I'm starting with a halide, and I'm ending up with a alkene. So I can take alkyl halides and I can make alkenes. I can also take alkyl halides and I can make alcohols, right? So if you want to think about this as a spider web, I could put an alkyl halide in the middle, and I could have a branch that goes out to alkenes by elimination. I could have a branch that goes to alcohols by substitution. And as we continue to study organic chemistry, you're going to add more and more branches to that web, okay? And you're also going to have a spider web, or a roadmap, as I like to call them, where you have an alkene in the middle, and what can I do to that alkene, okay? And it's a great way to study the different reaction types, is to build these roadmaps or spider webs, as some students call them, okay? Rearrangements. Why is that a rearrangement? The atoms have moved, right? The connectivity has changed, right? But notice I have one molecule on the left, one molecule on the right. I'm not adding anything to it. I'm not eliminating anything. I'm not substituting anything. I'm rearranging how things are connected, right? I am rearranging how things are connected. And so we can take one alkene and form another alkene. This is known as a rearrangement. It's also known as a transposition in some cases, not in this particular case. But you can move the functional group around within a molecule, is known as a transposition, which is also technically a rearrangement, okay? So notice the functional group is the same in this particular example, right? Alkene on the left, alkene on the right. Just how the carbons are connected are different, right? We can clearly tell by looking at this molecule that all the atoms are still there. We haven't added or eliminated or substituted anything. We've just reconnected all the carbon atoms in a different way to get a new product. So is this a functional group transformation? No. But it is a functional group transposition. We're moving it from one location to the other. Okay? Now, there are essentially two ways in which we can break a bond, because all reaction mechanisms, we're going to be talking about bond breaking and bond making. Okay? So we can have heterolysis, which uses a double-headed arrow. And what does that double-headed arrow tell us? I'm moving an electron pair, or two electrons, right? So I've got, and I don't know why, but every book does this. Start off with A and B. They don't even exist on the periodic table. Well, boron does, but. And we are pushing two electrons. What does that arrow tell me in words? Pardon? Technically, I am doing ionization. What else does it tell me in words? B is more electronegative. How do you know that? Electrons are moving to B, right? What else is this telling us in words? Pushing B out. I mean, that's not untrue, but I don't know if it's terribly descriptive. What's an ionic bond? That's a covalent bond to start with, right? It could be a polar covalent bond. We don't know because we really don't know the electronegativity difference, although Sarah suggests to us that B must be more electronegative than A because of the direction of the arrows, and I think that's a good observation. This is telling us that the bond between A and B is being broken, right? We are breaking that bond. And so does this require energy or does this release energy? It requires energy. And remember, all bond breaking events are endothermic. All of them. Even when you get to your biology class and they start talking about breaking the ATP bond and releasing energy, that's not technically true. Okay? Yes, ATP is an energy molecule, but it's not the breaking of that phosphorus bond or that ATP cleaving off that phosphorus that does that, okay, in and of itself. There's other steps that are involved in the release of energy, okay? I can also imagine doing this in a homolytic fashion where I use a fish hook, as we call it. What does that tell me in words? Typically, this occurs from two atoms that are connected together that have similar electronegativity. It doesn't have to be identical, but very similar. Okay, that's a good observation. What else? What else is this telling me?
Breaking the bond, but there's not really a pair of electrons moving. You got electrons going different ways.
Okay, so we have the single fish hook, right, or single barb arrow, tells me that I'm moving one electron from the bond to B, and I'm moving one electron from the bond to A. And we end up with what are known as radicals, okay? Not the political kind, the chemical kind.
Does that require more energy, moving electrons separate from each other?
Not necessarily. There are some bonds that are so weak that they will break quite easily without putting in a lot of energy. Now, you got to put in energy, okay, but you may not have to put in a lot of energy. And you all are familiar with a molecule that likes to do this. Hydrogen peroxide. This is how hydrogen peroxide works. It generates free radicals. For those of you in polymer science, if you've ever made a polymer, you've probably done free radical polymerization. And the initiator is a molecule that has one of these weak bonds that can readily, under heating or shining a light on it, whatever the case may be, break and generate free radicals, which then initiate the polymerization process. Okay? And we're going to learn more about free radical chemistry when we get to chapter 10. Most students understand this process pretty well. Okay? And fortunately, about 90% of the stuff that we'll talk about in this class can be thought of as moving 2 electrons at a time. Okay? However, in biology, most of what occurs occurs in a free radical process, interestingly enough. So for example, as you age, your aging process is because of a free radical process. For those of you who have ever heard of age-defying creams, what do they always say they have in them? They're rich in antioxidants, which prevent that process from happening, right? So it turns out in biology, it's this homolytic reaction process that's responsible for a lot of stuff. Not everything, but a lot of stuff. And it has to do with the fact that we're water-based. Water's a pretty good acid. And when we're moving 2 electrons at a time, we generate bases, right? B minus would be a base. It's a Lewis base. It's an electron pair donor. Not going to hang around in water very readily, okay? So that's why free radical chemistry is so prevalent in biological processes. When you learn about a lot of metabolism, a lot of that is free radical chemistry, for example. Now, you all are familiar with the Bronsted-Lowry theory. You're familiar with the Arrhenius theory from general chemistry. And you should also be familiar with the Lewis theory. Okay? Lewis is the big umbrella. Right? Does anybody remember what Lewis theory, what it states? What is a Lewis acid? An electron pair acceptor. Right? And a Lewis base is a electron pair donor. And so if we're thinking about things as Lewis acids and Lewis bases, what arrow would we use? A single barb or a double barb? A double, because we're talking about pushing a pair of electrons, right? The Arrhenius theory was anything that you place in water and it forms H plus is a Arrhenius acid, right? What's an Arrhenius base? Forms hydroxide. So Arrhenius came along with this theory and thought that all acids were proton donors and all bases were hydroxide donors. So no matter what it was, if I placed it in water, I was going to get H plus or OH minus, right? Now that theory jives pretty well, if you will, with what you talked about in general chemistry, right? Because everything that you all were telling me about the acids and bases that you knew about were either proton donors or hydroxide donors, right? But a proton can accept how many electrons? H plus, how many electrons could it accept? 2. So it's technically an electron pair acceptor, right? Hydroxide has lone pairs around it, so it is an electron pair donor. Okay, so you can see how Arrhenius theory really is just a subset of Lewis theory. Now Bronsted-Lowry came along and expanded that a little bit, right? And so according to the Bronsted-Lowry theory, what is a acid? It's a proton donor. Very similar to what we have for Arrhenius. But the difference is in the base, right? So what's the base to Bronsted-Lowry? A proton acceptor. So Bronsted-Lowry came along and started thinking about this in terms of protons. Lewis came along, G.N. Lewis, who a lot of people say should have won a Nobel Prize for a lot of his theories. Think about the things that you talk about. Lewis acids, Lewis bases, and Lewis structures. Kind of a lot of what we talk about. The guy was shunned for a Nobel Prize. Okay? Apparently he was not very easy to get along with. As I've heard. I don't know. He was dead long before I was born. But Lewis's theory was really the more consistent with chemistry because chemists are always interested in electrons, right? And basically what Lewis said was, forget the atoms. They're not important. What's important are the electrons. And an acid, if we look at them, they're going to be an electron pair acceptor. And a base is going to be an electron pair donor. And so that broadened acid-base theory to include organic compounds. So if we look at an example here, this is morphine, right? What do you know about morphine? Gets you really high. Can be converted into heroin, and that's true. It is it's not just a pain reliever, it's a massive pain reliever, right? I mean, people who are on morphine drips are usually terminally ill patients. It is a drug of last choice for pain treatment because it is highly addictive, right? But if we look at that, let's start off. Name for me the functional groups. Where are the functional groups? We've got an amine. What kind of amine do we have? Primary, secondary, or tertiary? You sure? There's one carbon-nitrogen bond, there's another carbon-nitrogen bond, and there's a third.
What is that?
It's showing that it's coming out of the plane of the board. It's showing some three-dimensional structure to it. I have the OHs, so those are alcohols, right? So these are alcohols. They're attached to an aromatic ring, so we technically call them phenols, but they are alcohols. What else do we have? We have an ether. What else do we have? Okay, we've got the alkene, right? And what do we have here? Benzene ring or an aromatic ring, and then we've got some just normal, carbon connecting it all together, right? So we take a couple alcohols, an ether, an amine, and an alkene, and an aromatic ring, and put them together. You've got morphine, right? But you got to put them together just like that. Now, it turns out that morphine contains acidic sites, and it contains basic sites. The hydrogen of an alcohol, like this, okay, well, this is a phenol, has a pKa of around 10. To an organic compound, that's pretty acidic. Okay? So these are actually acidic sites. These protons can be donated under certain conditions. The oxygen of the alcohol has lone pairs, so technically they could donate a pair of electrons to something, right? They are basic sites. The amine is a basic site. The alkene is a basic site. Why would the alkene be considered a base? There's a pair of electrons in there, right? But why the alkene and not the alkane? The alkane is held together by 2 electrons too, right? It is easier to break a pi bond. What else? What else do we know about pi bonds versus sigma? They're out of the plane. That's right. So if I think about a sigma bond, right, I've got 2 carbon atoms with the electrons in between. Nothing else can really get to them. But now I've got my sigma bond, and now I've got a pi bond coming up out of the plane of this, right? Another atom can come and interact with that pi bond. So pi bonds are actually considered to be bases. And the aromatic ring having 3 pi bonds, as we've got it drawn anyway, you can clearly see why that's a basic site. Okay? You need the acidity in certain areas, and you need the basicity in certain areas for this drug to interact with its receptors to give you the pain relief effect that you're after. Okay? So it all comes down to acids and base chemistry. One of the most important things that you will ever learn in chemistry is Lewis acid, Lewis base chemistry. If you understand your Lewis acid, Lewis base chemistry, you can wing it through most of your chemistry classes. And you'd think I'm kidding. When you get to biochem, you're going to learn all kinds of terms, and one of these days the light bulb will go off and you'll go, that's just an acid-base reaction. A lot of the reactions that we're going to be learning in here, you'll be trying to memorize them step by step, and one day the light bulb will go off and you'll go, that's just an acid-base reaction. And when that happens, you will know 90% of everything that I know. The other 10% comes from years of experience, and you'll get that with time, okay? But if you can break down most of chemistry into nothing more than a reaction between an acid and a base, you're in really good shape, okay? And that's a simple concept, but it takes a little grasping to get really good at it, okay? Sir?
If it has a pi bond, is that automatically, like, if it only has, like, a double bond to make your base?
It is a Lewis, it can be a Lewis base, yes. So let's take a simple reaction, and let's look at the, let's see, you're going to have to turn around here. I think we need a little room. So I'm going to draw water correctly. That is not water, right? So let's give it its bent shape. And if I take NH2 minus, which is known as amide, which is spelled exactly like amide, but it is pronounced differently. Go figure, right? What is the acid and what is the base? Water is the acid, and amide is the base. Now notice the mechanism. I'm pushing what type of arrow? A double-headed, right? And so I'm going to start at one of the lone pairs on the nitrogen. I'm going to push that to the proton, or to the hydrogen. How many bonds can hydrogen have? One. So this is telling me I'm making a bond between nitrogen and hydrogen. I can't have two bonds, so what has to happen? I have to break the bond between the hydrogen and the oxygen. And that, again, is a double-headed arrow. And so I end up with NH3 plus hydroxide. Everything has to balance on both sides. So I have my acid, my base, and now I have my what? What is ammonia? In this reaction, it's the conjugate acid. And hydroxide is my conjugate base. Remember, the acid goes to conjugate base, and base goes to conjugate acid. Okay? So you will always have an acid, conjugate base pair. Okay? This is the reaction mechanism. If I had to describe that in words, what is that telling me? It is telling me that as the two molecules come together and collide, right, the basic amide has a lone pair of electrons that are forming a bond with the hydrogen, and the bond between the hydrogen and the oxygen are breaking. And it's actually occurring kind of in a simultaneous fashion because I have both arrows drawn at this kind of the same time.
What actually breaks the bond? Like, is there something that actually breaks it? Is it just...
Yes. And this is one of the flaws of arrow pushing. Arrow pushing is a formalism. The reality is it's all about molecular orbitals. So remember all that from Gen Chem? We're not drawing all the molecular orbitals, which is good, all right? Which kind of hurts people's head. But technically what's happening is, right, these electrons are actually occupying an anti-bonding orbital which breaks the other bond. That's what's happening to break that bond. Okay? But in organic chemistry, we can just pick this by arrow pushing, and it becomes a lot easier to think about. Okay? Here we have hydrochloric acid reacting with methanol. Alcohol is functioning as a base because it is an electron pair donor. We end up with the conjugate base of chloride, and the conjugate acid is the protonated alcohol. Okay? Conjugate or acid, conjugate base, base, conjugate acid pairs. Okay? So what is the conjugate acid of ammonia? Pardon? Ammonium, NH4 plus. What is the conjugate base of methanol? CH3O negative. It's known as methoxide. What is the conjugate acid of CH2CH2? That was a little trickier. When we made the conjugate acid of ammonium, what did we do? Or of ammonia, excuse me, to make ammonium, what did we do? We added a hydrogen, right? How am I going to add a hydrogen or a proton to that? All right, so I start off with this, right? And I'm going to add a proton to it, and I'm going to get, but I'm not showing everything. What else do I need to put? Formal charge, and that has a positive formal charge. It's known as a carbocation. We'll learn about that in chapter 6, I believe. Okay? Very reactive. What's kind of weird about carbocation? What's weird about it? It looks weird. That's true. But why does it look weird? No octet. Carbon is at a place where we cannot exceed the octet, but we can have an octet deficient carbon. It's known as an intermediate. It's not very stable, but they do exist for very brief periods of time. For those of you in polymers, you've probably heard about cationic polymerization. You're forming cations. Okay? They don't live very long, and that's why the reactions go quickly, right? But it is the reactive intermediate in the process. Okay? Now, when I take acids and bases, I know they're all not of equal strength, right? You all learned that if you take HCl, HBr, and HI and you place them in water, they completely dissociate. You called those strong acids, right? So that means that HCl, HBr, and HI are all of this equal acidity, correct? In water, that is a true statement. Solvent matters. In organic chemistry, we rarely do our chemistry in water. HCl is a weaker acid than HBr, and HBr is a weaker acid than HI in organic solvents. Okay? Remember the trend, our periodic trend. As we go down a family, right, acidity increases. Okay? Now, you all learned this simple equation. HA plus H2O goes to A minus and H3O plus in general chemistry. And you all learned about this concept of an equilibrium constant, right? KEQ. If KEQ is greater than 1, the equilibrium lies to the right. If KEQ is less than 1, it lies to the left, right? Left. Correct. Okay. So, and we also learned that KEQ is going to be our products over reactants, right? And so what are my reactants? HA and H2O, and my products are A minus and H3O. And you all probably learned that you could just miraculously let water fall out of the equation. How many people learned it that way in high school or somewhere else? That we just ignore pure liquids, right? Yeah, we lied to you. What assumption we can make is that since water is the solvent, does its concentration really change much in that reaction? No. So what we can do is we can pull it out of the equation and call it something else. And that something else is Ka. The acidity constant, Ka, is equal to KEQ times the concentration of water, which is equal to H3O A minus over HA, which is the same thing as saying, oh, just let it fall out of the equation. But we lied to you mathematically. You all should have been really upset with your teacher when they said, oh, it just drops out of the equation. If something is equal, you can't just let something go nowhere, right? It's no longer equal, right? But we play a little trick. And that trick is that at low concentrations of acids in water, the concentration of water essentially remains unchanged. Does anybody know what the concentration of pure water is in a flask? It's about 55.5 molar. If I have a liter of water, I have about 55.5 moles of water. So if I add 1/10 of a mole of HCl, have I really changed the concentration of water that much? Not at all. So this is a fair assumption to make. So we just do a little algebra, right? I don't let it just drop out. I just simply multiply this side times water, and I multiply this side times water, and I take water times KEQ, and I call it Ka. Ka is not KEQ. It is related, but it is not identical. Okay? Now, your typical ranges for PKA, well, here we got Ka values, okay? So for organic acids are going to be 10 to the negative 5 to 10 to the negative 50. So does that mean that most of these acids have an equilibrium that lies to the right or to the left? To the left. Organic acids are typically fairly weak, and they don't completely ionize when placed in water. Now, most people don't like dealing with this type of math, so we just take the negative log of it, which is called P, and we call PKA values. So I know that the lower the PKA value, the stronger or weaker the acid. The stronger. And the higher the PKA value, the weaker the acid, which also means that its conjugate base must be really strong. We have bases in my laboratory right now that have a pKa of around 50. That's strong. And if I take them out of their bottle, put it in a syringe and squirted it out across the room, a green flame would happen. Okay? It's that reactive. They're that strong of a base. Okay? So, we're dealing with new realms of acids and bases. Okay? That's the take home. Organic chemistry is not as quantitative as your general chemistry was, right? You were always solving some type of equation. You were always worried about significant figures, yada, yada, yada. Fortunately, in organic chemistry, if you're pretty good with numbers and you can get close enough for government work, you've got it, okay? We usually don't care to the third decimal place, all right? But what I want you to know is the rough ranges for things. I want you to know that if Ka is greater than 1, the ionized products are greater than the intact acid. In other words, the equilibrium lies to the right. If Ka is less than 1, the opposite is true. If Ka is much greater than 1, let's say 1,000 times, we say it goes to completion. Okay? And if Ka is really tiny, let's say 1,000th, then we say, the reaction doesn't occur. Those ranges you're going to have to kind of have a feel for. And by the end of this class, you will be able to look at a reaction and be able to predict which side the reaction lies without me giving you a bunch of numbers to figure out what the Ka's are, or the KEQs, I should say. Okay? Here are some examples. I do not expect you to commit the entire list to memory. HCl has a pK of -7. Acetic acid is just under 5. Water is just under 16, which is very similar to alcohols. So what could I predict then? If I know the chemistry of water, I probably also know the chemistry of most alcohols. Surprise, surprise. In fact, alcohols are nothing more than organic derivatives of water. So if I know the chemistry of water, I can predict the chemistry of alcohols. Because guess what? The functional group is essentially the same. You just get rid of 1H. That's right. We know that water can function both as an acid and a base, so I know that an alcohol can function both as an acid and a base, right? So you already know a lot of stuff. Hydrogens on carbon-carbon triple bonds have a pK of 25. Hydrogen has a pK of about 35. Ammonia has a pK of around 38. Methane has a pK of 50. Right? So very, very weak acid, but the conjugate base of this must be a very strong base. And we have solutions of what's known as methyl lithium, which is essentially, you can think of it as CH3 minus. It's a very, very strong base, and guess what we use it for? It's a very, very strong base. So if we have a very, very weak acid we're trying to react, we react it with a very, very strong base. Okay? I don't care that you know the exact numbers, but you should know, that a carboxylic acid is going to be around 5, an alcohol is going to be around 16, an alkyne is going to be around 25, the mid-20s, and other things are going to be much greater than that. You should have a feel for that. Okay? So for example, if I took methane and I reacted it with chloride, would you expect a reaction to occur? If I took gaseous methane and I threw in some Cl minus, would a reaction occur? And why not? All right, I have an extremely weak base reacting with an extremely weak acid. The equilibrium will not lie to the right. And I can get that just from this PKA argument stuff. Okay? Again, acids and bases, the most important thing that you ever learned about in general chemistry, and you probably spent the least amount of time. We had you worrying more about gas laws and other stuff, when in fact, half your time should have been studying acids and bases. Because we think you need to know everything for some reason, right? I'm not trying to belittle it. I mean, the other stuff is important, and you're going to learn more about a lot of that when you get into analytical and when you get into PChem and those types of things. But the reality is, for those of you who are in biology, it's all acids and bases, and you really need to know your acids and bases, okay? So, what makes a strong acid, and what makes a weak acid, and what makes a strong base, and a weak base, a weak base? Did I say that right? Yeah, okay. there are some factors that come into play, but the number one thing that you need to remember is that anything that stabilizes the anion makes the starting acid more acidic. So, let's use the generic HA. And that dissociates, right, to give H plus and A minus. Anything that can stabilize A minus is going to make that reaction go in that direction. In other words, going to make this a stronger acid. Okay? And there are a few factors that come into play with that. There's the element effect. There's the inductive effect. There are resonance effects, and there are hybridization effects. So anytime I give you two acids and I ask you which one is the strongest acid, what are you going to do? You're going to take both acids, you're going to dissociate them, and you're going to look at the anions. And you're going to say, this anion is more or less stable than that ion, and therefore that must belong to the stronger acid. And it's always going to come down to element effects, inductive effects, resonance effects, and hybridization effects. So no matter what factor you have to take into account, the process is always the same. You're going to draw the conjugate bases, the A minuses, and you're going to ask yourself, comparing these things together, which one is the more stable. Okay? So, let's look at element effects. Element effects are like looking at what element bears the negative charge. Okay? Now, if we look at the period, the second row, right? What do we see as we go from left to right? We increase acidity, right? We increase acidity as we go from left to right. You learned that in Gen Chem. But you didn't learn that it was an element effect, did you? You just learned the trend that as I go from left to right in the periodic table, my acidity increases. And that'll work for you 99% of the time, but it doesn't tell you why, right? Why is that? Because if we look at the conjugate basis, what would the conjugate base for this molecule be? It would be, they don't really put CH3 there, right? They just put some sticks. But so it would be that. What about for the next one? What about for the next one? And the last one? Why does this explain it? Are they? As I'm going this way, larger molecules actually are more stable. That has to do with the family effect, not the period effect. We'll talk about that tomorrow or Friday. What about it? The atom bearing the negative charge, we're looking at electronegativity. Carbon is less electronegative than nitrogen, nitrogen less electronegative than oxygen, and fluorine we know is the most electronegative. So if I'm really electronegative, am I going to like to have a negative charge or not? Yes. And we're going to stop there today. We've run out of time. On your way out, just put your inverted lecture on up front. And I will see you all on Friday.